Good morning, everyone. I'm Natalie, the Heme Queen, here with a blood drop, the first of a few, on sickle cells. And this one starts with Miles Davis. When I was in medical school, I was studying a lot, no surprise, and I needed something in the background because I hated silence. So sometimes I'd have TV in the background, sometimes I'd have classical music in the background, but my favorite study companion was jazz. And so it was during medical school where I first really heard and learned to love the music of Miles Davis here on this stamp. So I collect stamps. I have a whole stamp collection. You'll be seeing a bunch of my stamps in this video, on my TikToks, and on my online lectures. I love sprinkling them into the stories that I tell. This image is my absolute favorite of Miles because I just see him with his trumpet and he looks like he is just lost in his craft and delivering this amazing music. And I got an even greater appreciation for this image recently when I learned that Miles had sickle cell anemia. And this caused him a lot of hip pain, like horrible, debilitating hip pain. And so now when I see this image, I see him bending backwards. So I'm thinking maybe he had some hip pain, but yet here he is, creative genius, giving his gifts to the world, entertaining us despite likely being in a lot of pain when this image was taken. How did Miles's sickle cells cause him so much pain? Let's create a 3D model. We'll start with a femur here on the right. So the femur is the long leg bone, and the top of this bone is what's going to connect to the rest of the body, creating our hip joint. And let's add a blood vessel to feed that bone. And we're going to have to add some blood, but we're only going to have red blood cells here. And let's just stop halfway for now. Red blood cells. After I graduated medical school, I went into pathology residency. So about, eight years ago was my first day of my hematology rotations. Like we rotate through all these different labs. It was my first day and I walk into hematology, the blood lab, and I was so excited. It was like the first time I was gonna look at blood under the microscope on my own, because before then I only saw pictures like in a textbook or in a lecture. And so now finally I was gonna hold the slide and like look at it myself. And so I take my first slide, I put it under the microscope. I think even before I put on the microscope, I was like, oh, maybe I will diagnose a patient here in the hospital today, which was ridiculous because I really didn't know much then. I also did not know I was going into hematology. So I look under the eyepieces and I see something like this. This is a 2D rendering of what I saw. And I have to admit that I was really disappointed. I was looking at the red blood cells. They took most of the space here, most of the real estate, and they looked absolutely boring. They were circular and they were one color, like they were just red with this like center paleness. And I was kind of like, oh, that's it? I mean, I loved the white blood cells. They were really cool and the fuzzy platelets were really pretty, but the red blood cells, I was a little bit unimpressed with. Let's look at them in 3D. If you had showed me this back then, I probably still wouldn't have been impressed. But today I'm absolutely fascinated by this red blood cell. Yes, it's one color, and yes, it looks a little bit boring in shape, but it is so cool, and let me show you one of the ways that it is so cool. Back to our femur and our blood cells that are trying to get to the femur. If you look up close here, the red blood cell, the boring red blood cell, it's pretty big now that we've zoomed in. A red blood cell is between 7 and 8.5 microns in diameter. Now, it has to squeeze into the smallest of blood vessels, which are capillaries, and capillaries can be 3 microns in diameter. This red blood cell has to find a way to get itself into a tunnel that is a third of its size. Here is the red blood cell from the front, here is it from the side. How is it going to fit in? And the way it fits in is that it's very deformable. It can bend, it can twist, it can do a somersault, which allows it to fit into that teeny tiny capillary. It is able to reach that femur and supply it with oxygen. Now, sickle cells, on the other hand, cannot do this. So if they approach this teeny tiny capillary, they don't bend. They are actually going to get stuck, and then a bunch of them can get stuck, and then all the cells behind it will get stuck, forming this clog. And then this clog prevents blood or anything from getting through to the femur, in this case, or any other parts of the body. Now this causes extreme pain. The number one symptom of sickle cells is pain, and this is the reason behind it. It's this sickle clog, also known as vaso-occlusion, meaning occluding the blood vessels. Now this pain can last a few minutes, a few hours. It can be a one-time thing in that area, or it can keep reoccurring and becoming chronic. Now, if it lasts too long, it can actually fully deprive that tissue, in this case our femur, of oxygen for way too long, and in that case the tissue will die. And so here I've illustrated that out by this like black kind of dead tip of the bone. Let's head back 20 years before Miles was even born to meet Walter Clement Noel. It was the day after Christmas, and Walter, a 20-year-old dental student living in Chicago, walked over to the nearby hospital. Walter had been coughing, was having chest pain, was feeling very tired, and getting very weak since Thanksgiving. At the hospital, an intern named Dr. Irons was taking care of Walter, and one of the things he did was look at Walter's blood under the microscope. And he was completely baffled by what he saw. And since it's the day after Christmas in Chicago as this was happening, and since it's very cold here today, I decided to use snow as our background. We'll add a glass slide and first look at normal. So here are those seemingly boring, but not boring at all, red blood cells. They are disc-shaped and they all look like one another. This is what Dr. Irons saw. He saw a couple of normal cells here and there, but he saw a lot of these stretched out, elongated, slightly bent cells that looked like little half moons. He immediately wants to tell his attending Dr. James Herrick. So I totally picture this, like as if I was the intern, like, Dr. Herrick, you have to come see this blood smear. Dr. Herrick looks under the microscope and is also equally baffled at what he saw. He has never seen cells like this before. Eventually, Walter recovers and he's discharged. And a few years later, Dr. Herrick publishes a photo of Walter's blood in a medical journal and says something like, I saw this, I don't know what these cells are, I don't know what these cells mean. In the years to follow, some other reports came out of different patients having very similar findings to what Walter had in his blood. And by 1922, these cells got the name sickle cells, named after this farm tool, the sickle. But no one knew what caused sickle cells, and we'd have to wait another 20-ish years until we would meet Dr. Linus Pauling, a chemist and a 2-time Nobel Prize winner. Dr. Pauling thought that the problem with sickle cells was in their hemoglobin. Hemoglobin is a molecule that's found in red blood cells. There are hundreds of millions of hemoglobin molecules in a single red blood cell. They are the molecules that pick up, carry, and then deliver oxygen throughout the body. He hypothesized that the hemoglobin inside sickle cells was different from the hemoglobin found in normal red blood cells. Normal disc-shaped red blood cells are full of hemoglobin A, and he thought that the hemoglobin in sickle cells was different from hemoglobin A. And he ends up proving it, and if you want all the details on that groundbreaking experiment, I posted a YouTube short on that, so you can check it out. So let's look at the hemoglobins side by side. Hemoglobin A is on the left and hemoglobin S is on the right. Now remember, hemoglobins grab oxygen, so here they are fully oxygenated with these blue oxygen bubbles, and then they release them throughout the body. Dr. Pauling discovered that the hemoglobins were indeed different, and the difference is really small. Let's find the difference between the hemoglobins. Hemoglobin is made up of 4 globins or proteins. Both hemoglobin A and S have 2 alpha globins here in yellow, and they have 2 beta globins here in orange. So where is this difference? The difference between these 2 hemoglobins lies in the beta globin. If we flip over the hemoglobins, you'll see that the beta globins of hemoglobin S have these pockets that aren't found on hemoglobin A. And it's this pocket that makes the beta globin of hemoglobin S different. To keep things simpler, I'm going to change the beta globins of hemoglobin S to green. Hemoglobin S was truly different from hemoglobin A, as Dr. Pauling correctly hypothesized. Dr. Pauling took it a step further. After proving that the 2 hemoglobins were indeed different, he hypothesized that the difference was in how those beta globins were made. Let me show you that. We've got our two different beta globins here. Globins are proteins, and proteins are made up of amino acids. So if we look at what these globins are made of, they are made of 146 amino acids. So Dr. Pauling thought there was a difference in the amino acid structure that made the beta globins different from each other. But it was another scientist who confirmed that, and his name was Vernon Ingram. So both beta globins are made of 146 amino acids in total, and that one change is the difference that separates the two of them, and it's the 6th amino acid. This single amino acid is what causes sickle cells. Normal hemoglobin A likes to stay separate. It likes to stay apart. Sometimes I think of the hemoglobin A as apart. Even if you put the hemoglobins closer together, they don't like to get close. However, hemoglobin S is more stacky or sticky, and it's because of this pocket. This pocket on beta globin is abnormally attracted to the alpha globins of other hemoglobins. If you push these hemoglobin S's together, let's say you shrink the cell or there's low oxygen around, they will start stacking and form these long rods that will change the shape of the red blood cell from this to that. If a single amino acid is the problem here, if it's a single ingredient change, what went wrong with the recipe? Like, what is the recipe? And that recipe is DNA, and I'll talk about it in an upcoming video. I got a comment on my last TikTok asking, how does it affect your health? And actually someone replied to it. The sickle cells get stuck in the smaller blood vessels, causing excruciating pain and lack of oxygen to that area. There are a lot of problems that sickle cells cause. And back when I was in medical school, listening to Miles, I started out by memorizing a lot, and that didn't get me really far. When it came to sickle cell disorders, I remember having these long lists of problems because sickle cells cause a lot of problems. When you think about it, sickle cells are in blood, and then blood flows everywhere in the body, so theoretically sickle cells could cause a problem anywhere in the body. But there's really two main effects. The first one has to do with the cell itself. That cell is really fragile, so it can burst in the blood, or it can look so damaged that it gets scooped up by the spleen. So the first part is that sickle cell not lasting to its normal 120-day lifespan. And then the second one is what you've been seeing, what you saw with Miles. It's those sickle clogs or vaso-occlusion. So you've already seen that sickle cell can't fit into those capillaries, they get stuck, and then it causes all the cells behind it to get stuck, depriving tissues and other parts of the body, bone, of the blood and oxygen that it needs. And this vaso-occlusion can occur anywhere. So I've shown you the bone. Another part of the body that this vaso-occlusion really affects is the spleen. These sickle cells can get clogged in there, or you can get a clog that supplies the spleen so that a part of it might die off, causing infarctions. So the spleen is especially vulnerable to this. The bottom line is these clogs can affect anywhere in the body, and they cause tremendous pain. If you enjoyed this video, please hit the like button. I love comments, so please leave your comments, especially if you have questions. And also, there are upcoming videos on the genetics of sickle cells, like the DNA explaining sickle cell trait versus sickle cell anemia. And I also have a bit on the malaria theory coming up as to how this sickle cell mutation came about and keeps getting passed down. So be sure to subscribe so you don't miss any videos.